think I'm live. Um, I hope the audio is fine. I'm not really 100% sure. Let's see, can I mute? Is there a button here? I don't think so. Maybe not. Let me see if everything is working. It seems like it is. Hello everyone. So this will be a stream that is like not at home. I'm at my dad's place, but I think we can still do like a good stream. Like, I don't really have second monitor, so I guess I'll just read chat from this. I can't otherwise see chat. Or maybe I can look at my phone actually. Then I can only look at Twitch or YouTube. Let me open it up on my phone. Second setup, indeed. Hello, Just Crime, welcome. Nice. I guess I can look here then. So, well, I plan to do some. Okay, wait. I need to be careful so I don't leak anything. Let me open OBS and let me just close this a little bit. And let's close this. And this. Okay, is the audio like bearable at least? Watching a movie, so gotta go soon, alright. What movie are you watching? Did you see my Twitch clip? No, I didn't actually. I have not seen it. Audio is decent? Alright. Let me hear. Okay, it's kind of rough. Not the best audio. But yeah, it's from my laptop. Man, I should have probably brought my mic, but I thought the laptop would be decent enough, but maybe not. Some Detective Conan new movie. There's about 20 plus. But I finally reached the cinema, so watching with free tickets. Nice. Yeah, you do that every month, right? You get like a ticket, like a free ticket from your bank or something. What am I gonna be doing today? Hello, Kunsh and Samya. Well, the plan is to do some statistics. Apologies for the noise if you can hear children screaming. So I wanted to do a little bit about the cumulative distribution, which I did work on a little bit off stream. I did complete, I think yesterday I was reading about a couple of distributions, like continuous distributions, like the exponential one, and the normal, like standard normal distribution. And then I today read a little bit about cumulative distribution functions. And I think maybe, yeah, this theorem 2.5/2 over here. So I want to continue here, and then I want to do some Actually, I have no idea. Maybe some later analysis or something. Or actually, I should maybe prepare for my thing I have tomorrow, or Monday and Tuesday. Yeah, that's true. I'll do that actually. So I'll do some one variable stuff. Good memory, yeah. My memory is usually not that good. If I remember, I'll send a Twitch clip on your Discord server later. Alright. Cool. I'm excited what the clip is about. There were some, I think there were some good moments in the streams. I know I did some blunders, especially yesterday, during the late stream. But, I mean, yeah, anyway. Okay, let's start. By the way, I'm not sure if this full stream will be 3 hours. I'll do as much as possible though. But yeah. Okay. Alright. I'll work on my stats 2 document. It's actually, so now I've, like before I just wrote downwards, but now I'm actually writing, I have another column. Wait, is it, oh my gosh. Oh shit, what happened? Okay. Crap, I don't have a mouse as well. No. Ultra scuffed. To pan, press mouse wheel or mouse right button and drag. That's very convenient. No. Okay. Alright. Alright, so we have theorem 2.5.2. Perfect. Maybe I'll increase the audio a little bit. Can I? So f be a cumulative distribution function, and then we have some properties, which I guess we can try to prove ourselves. So we have that CDF. So we have, I mean, okay. I don't know, I mean, this first property seems very obvious. I mean, this is defined to be equal to the probability of x inside, oh no, sorry. Actually, oh yeah, so it's x less than or equal to x little x. And we know that probability function is always a variable from our sample space to 0, 1. Or maybe this is rather a sigma algebra, if you want to be correct, which is probably a good thing to be. Where am I? Wait. Can I zoom out? Fellow mathematics student, hello Vivian. We're doing some stats this stream. I think I've done, yeah, this says last stream as well, but I'm gonna move on after a couple hours, I think. Bro, where are my, let me refresh the page. I think, yeah, I'm zoomed in like crazy. Alright, I'll figure this out. Gosh, I'm so thirsty as well. f of x is increasing. Yeah, well, this one is very easy to... It's just inheriting properties from the probability measure. I'll just click this button. Or in your first year, Vivian? I was actually in I think I wrote this in the post I posted like on the YouTube channel a short while ago. I was in a nation meeting and surprisingly I met 2 fellow mathematicians there, which I haven't I've worked at the nation, and by the way, for people who don't know, in Sweden you have nations where it's like a fraternity ish type thing, and yeah, I found some fellow math people there, which was also very exciting. I'm just gonna look at the proofs. So that p theta, yeah, exactly. So the limit is 1. Right, we have continuity of p, which I am not really that used to. I don't really know that much about it. I mean, is it just continuous? Let me look. Looky, 1 point. Let's look at this. Right, so we just need to show it's increasing. And then we know it's continuous, right? So if we want to show the limit exists, yeah, n increases, hence by continuity of p. Then we have that. And we need to show that it's just decreasing instead of increasing. Alright, I guess that's fairly straightforward. So the right continuous. Turns out that if function satisfies probability 3D. Then there is a unique probability measure P on R such that F is the CDF of P. Right, what does right continuity mean? Okay, well, I guess, yeah, so if it's continuous on the right side. Then there's a unique probability measure. Alright, we want to compute cumulative distribution is for discrete random variable from its probability function bx as follows. Let x be discrete random variable, probability px, probability function, then its cumulative distribution function satisfies so it's the sum for all y less than some x, which makes sense, I guess. I mean, this is by okay, well, the probability is by definition equal to for all x less than or equal to x. Sum of this, which is yeah, okay. Is if x is a discrete variable, then theorem 2.53 is a piecewise constant with a jump of size at each value of that. A plot of such distribution looks like is depicted in 2.5.1. Consider only one fair six-sided die, so that this I mean, in this example, this would just be if and only if s is less than or equal to 6x. Show, okay, so x is a number shown on the die divided by 6. Okay, let me. Is equal to 1/6 the size of s when s is less than 6x. To compute f of x, we count how many elements and multiply that by 1/6. Therefore, k. Alright. See if this absolutely continuous distribution. Okay, cool. Right, so if something is absolutely continuous, it has a density function such that so it has a density function let me just think. Hello Lars, welcome. Welcome. Man, have I forgotten this? We have to have that a density function is like normalized, and it's a function from let me see. There are a lot of definitions, let me recall. I mean, what is really a bit weird is like usually for probability mass functions, I mean you write them like px, and then right, I guess you do like this, right? Which is defined to be probability of x being x. But in this case, as I understand, the probability density function is like the continuous version of the PMF. But here we don't really mention the random variable, which have to mention it somehow, right? That's why I'm a little bit confused. A tad bit. So it's normalized. I mean, yeah, it's just okay, fine. And then I see. That's all right. Okay, well, in its definition, it has nothing to do with a random variable having a density. Fine, I guess. Let's be x be absolute continuous variable, then x is a continuous random variable. Okay. I need to see the exercises. Okay, I guess I assumed like that the definition of a density would be correlated with a random variable, like the probability mass function is. I mean, we need a probability. We need a like a random variable. Okay. I mean, so it's not really analogous. I mean, right? All right. So let's continue here. Man, I want to get through this chapter, man. It feels like I've been stuck here for a while. Or maybe not necessarily the chapter, but I'm still kind of behind on on where I should be on the course, which is kind of unfortunate. Let me just check the audio. Maybe it's a bit too quiet. I'm not sure. I think it's hopefully fine for everyone. By the way, I do apologize for the audio. But yeah, tomorrow will be like a normal stream, so yeah. Okay, so we have that x is absolutely continuous random variable with density this, then the cumulative distribution function. Okay, so we have so apparently it's direct. yeah, I guess this is just and and we know that this can be described by density function. Yeah, so this is just like this. From the fundamental theorem of calculus, we see that it is also possible to compute a density function once we know the cumulative distribution function. Let x be the absolute continuous random variable with cumulative distribution function. Let dx, yeah. So if you want to do dx, it would be f of xx, right? And then f of x, fx is a density function for x. Right. We know that fx might not be differentiable everywhere, so that the function f of x of the corollary might not be defined at certain isolated points. The density function may take any values at such points. Consider again standard normal distribution with density phi given by that 2.4.9. Bruh, what is that? Okay, I'll just continue. According to theorem 2.4 for the cumulative distribution function, f of the distribution is given by it's fine. Alright, good. Good. So it is probably impossible to evaluate this integral exactly, or provably impossible, except for certain values of x. Nevertheless, the cumulative distribution function of is so important that it is assigned a special symbol. Furthermore, this is tabulated for certain x values. Phi stands for a cumulative distribution function of a standard normal distribution defined by Okay. Suppose that x is normal, you distributed, and we want to calculate the probability of that. Then is that, well, that is unfortunately cannot be computed exactly. We have approximated using a computer to numerically calculate it. Let's go to 5.2. Virtually all statistical software packages will provide such approximations, but many tabulations such as table 2D2 are also available. Okay. Bunch of approximations. and decimal expansions. Fantastic. Suppose that for this random variable we want to compute all these probabilities directly from f of x. Right, so you would find, I guess it's not differentiable everywhere, but we know this is true. Or maybe I should have an x here. But I guess between for x like this, right. Yeah. So here is differentiable, and so here, or wait, no, this is just, we can do this directly. This is just equal to 3. So this would just be equal to 3 minus 2, like that. Can you guys see this? Is it visible? Okay, seems good. Seems good. Okay, the other ones are. Or wait, no, wait. Let me just think for a moment. Oh yes. Is good, and then we can just, yeah, so this would just be f, like the CDF of 3.4 minus CDF of 1.2. It's stats today, indeed. Indeed. Man, I'm so thirsty. I should get some water. You know, I have this very bad habit of like being very lazy. I guess it's just laziness. But usually, like when I don't have water nearby, I know I'm very thirsty. I just can't bother to go up and get water. Yeah, it's very simple. Yeah, for some reason I wanted to find this density function, which is fine. I think you can do it very easily. Just taking the derivative. Okay. Since we're doing stats, let's say 3 coins are tossed and we want to find probability of 3 heads. So y is given by PHHH and not by PHHH x3, as we have 3 coins, so 3 different combinations. Uh, I mean, the sample space would be HHH. I mean, we have 8 possibilities, right? And I mean, you're thinking of that we can like we can have different order, right? But in this case, we don't really care about order. So I think, I mean, I'm not really the best at stats, but yeah, I'm kind of blanking, but yeah, I mean, if we did care about order, it wouldn't be 3, right? We would have 3 factorial, which is 6. Why do we care about order when we try to calculate something like probability of 1 head? So we calculate for head first, head in first, coin, then in second, then in third. Right, because then we, I mean, it's like, but in that case we have like a head, like we have head and tails. So, I mean, we don't care about order when it is with heads, but with head and tails we do. But yeah, I think that's just the nature of the problem. If it's 3 factorial and all 3 repeat, then it's just, which is 1, so does that mean there's only one combination? Well, like combination, why we don't think about order, it's just 1, yes. New setup? No, it's, I'm at my dad's place, so the setup is like bad. But yeah, I'll be back to my normal setup tomorrow. I mean, the nature of the problem is that we don't care about if we have like heads is like a a single thing, and we don't care about the order of them. So we want to talk about 2 heads and 1 tail. So it's that we have 2 heads. I mean, you would do from 3 pick 2. That would be the different ways of doing it. That would be the different ways of picking 2 out of 3. So is that equal to 3 factorial divided by 2 factorial? I actually don't remember the formula for it, but maybe. It would be 0, 1. I need to do the freaking triangle. So yeah, it would be 3, 3, 1, and this would be 6 divided by 2 is 3. I mean, yeah, it would be true. I don't remember the formula. There's some formula for it. Let's move on. Suppose now that f1, f2 are cumulative distribution functions corresponding to various distributions. P1 to pk be positive real numbers with blah blah blah. These values form a probability distribution, and we can define a new function g by I didn't really register. So we can define CDFs for discrete variables. Standard mathematics 2, let's suffer together. Let's go. If your question says 1.5 standard deviation of mean, what does that mean? I mean, I think sigma is just equal to 1.5, right? Like standard deviation. Okay, let me grab some water. And it's look good for the camera, not to procrastinate. 1 second, guys. water has been accumulated. It is represented that the function g given by 2.3.2.5.3 subcords a to d from theorem 2.5.2 and is right continuous, hence g is also a CDF. Probability distribution. So G is a so properties A to B, if I remember correctly, we have that needs to be okay, I don't remember. Be between 0 and 1 from x. Okay, so is this true? Yeah, it should be true. It should be true. Since each of these values is less than 1 and this is less than 1, so the sum or the product will be less, like, it will be smaller than each of the factors. So the sum will always be strictly less than 1, I think, right? Do you mean mean is 1.5? That'll mean it's 1.5. You can search up standard deviation of mean. It's denoted by sigma, and I think it's the standard deviation. It's just it isn't the mean, but it's rather the mean of the difference between the variables. So yeah, you can. I think you can ask like ChatGPT or whatever online. So you would have a mean, and you would also have a standard deviation mean. What book am I using? I'm using. It's actually linked in the description. I'm pretty sure. I think it's something not Vretblad. It was this one, Evans Rosenthal. Yeah, you can find a PDF online, which is very convenient. Yeah, I guess this isn't really like a rigorous proof. Um, I think there is a proof. I don't think it's very difficult. Oh no, there's no proof. It's just okay. Oh, it's an exercise. Okay, well, the function g satisfying a to b. Okay, the distribution whose CDF is given by 2.5.3 is called a mixture distribution because it mixes the various distributions with CDFs. Of course, according to the probability distribution given by p1, p2. To see how a mixture distribution arises in applications, consider a two-stage system, as discussed in 1.5.1. Describe the outcome of the first stage and such that pz is equal to I is equal to pi. I see. Suppose that for the second stage we observe a random variable y. The distribution of y depends on the outcome of the first stage, so that y has CDF of I. Mixture distribution. Blah 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 blah. So we have two bowls containing chips. Bowl 1 contains one chip labeled 0, two chips labeled 3, one chip labeled 5, one chip labeled 2, one chip labeled 4, one chip labeled 5. And then we drawing a chip from bowl number I. This one has a distribution function. Yep. Suppose that we choose a bowl by randomly selecting a card from a deck of 5 cards, where one card is labeled 1 and 4 cards are labeled 2. Let's denote the value on the card. Observe I, Y by randomly drawing a chip from the bowl. This is a mixture of the CDFs. Ooh. I see. So it's so the mixture is of the CDFs. Okay. Wait, is F1 CDFs? Wait. This is a measure of the CDFs. Well, F1 is, or evaluated at x, is all y is less than or equal to x of wait, was it the probability of these, or yeah, so we would, okay. Exactly. It would be the probability of. Wait, I'm a little confused here actually. Am I using book for a specific course you're taking or just studying for fun? No, I'm doing it for a statistics course. Yeah. Yeah, so this is the course literature. For one contains one chip labeled 0, two chips labeled 3, and one chip labeled 5. So 0, 3, and 5. Yeah, it makes sense. Sorry, that took way too long to get, but yeah, it makes sense. It just confused me a little when it says that x1 has distribution function. They mean commutative or cumulative distribution function. So that makes sense. And then that would be one card is level 1. Sure of CDFs applied. I'm not sure if I'm completely convinced. For in the bachelor's here, I'm currently doing my master's in applied mathematics in Denmark. I'm in my second year currently. So yeah. Right now I have a ODE course, and I have this math stats course, and then I have a one on linear analysis, or I say Fourier analysis since it's easier to understand, I guess. But I guess more general description would be linear analysis, since we're not only doing Fourier stuff. But yeah. I mean, if you're doing applied, you're probably laughing at me right now. I'm sorry. No, but you're probably way better than me at stats. Because I mean, most likely, if you're doing applied, you're good at stats. At least that's my assumption. But I don't really know. Location and scale mixture. Suppose f is some cumulative distribution function. Discrete location mixture. Okay, I'm not really sure if this mixture stuff is getting into my brain. Itself correspond to a special case of a discrete location mixture. Furthermore, if G is non-negative function, so G is a density function, we then define okay. So this looks a little similar to like a convolution. Then it is not hard to see that H is also a cumulative distribution function, one that is called a continuous location mixture of F. The idea is that H corresponds to a mixture of different shift distributions Fy with the density G, the distribution of the mixture. You can also find a discrete scale mixture Biscuits, okay. A K is also commuted to call a continuous scale mixture. You might wonder at this point whether a mixture distribution is discrete or continuous. Okay. The answer depends on distribution being mixed and mixing distributions. For example, discrete location mixtures of discrete distributions are discrete, and discrete location mixture of continuous distribution. Okay, I guess I need to read through this again. I've heard a lot of I've had a lot of probability theory and some statistics, but it has been 2 years since I had a stats course. Oh, okay. Wait, 2 years? Alright. What are you doing? Like, what are you working on then? I mean, when I hear applied, I just think stats immediately. But I guess, I mean, maybe some physics, some other stuff. Okay, so what is a mixture distribution? Let's just I didn't really activate my brain when I read this. Hello NN18. You progress a lot in the book since last stream. I did do some stuff off stream. We're doing mixture distributions and location scale mixtures. It's like, okay. Right, so we did a mix distribution. Okay, right. So no, I don't mean this, but a location mixtures, because this is a mixture distribution. Yeah, and also I'm not really sure if I'm completely convinced here, but I think I'll do some exercises and hopefully this will click once I've done that. Wait, hopefully you're doing well, NN18. Hopefully things are good. I mean, the last couple of days has been kind of like, channel has been kind of stagnant, not gonna lie. But I do want to do more content, honestly, like more of these streams, but yeah. Life got in the way. So am I convinced that this is this a CDF? I mean, this notation is getting under my skin. Not gonna lie. Right, so this needs to be well, I mean, the definition of this is just isn't. Wait. Ay, ay, ay. Personally like the streams. Nice to hear that. I'm liking them as well. Not to say that they're good, but I'm enjoying making them. I mean, this stream is specifically scuffed, but I'm also moving out soon, so things are gonna be a bit messy. Maybe. I'm not really sure the internet speed in the new place as well. But that will happen in a couple weeks, maybe 2 weeks. But I mean, is there like, okay. Yes, it's shifted by y. So PI form a probability distribution. I guess so. I mean, it seems weird saying that we have probability distribution without having a specific random variable, but I guess it's fine. If you look at the picture below, you should just be able to convince yourself that it is a distribution function. Yeah. I mean, like saying something is a CDF is basically saying nothing, right? I mean, it's just notation. This seems very unnecessary wording, like a CDF is just a way to write a probability, like saying it's less than this. It's like seems a bit weird. Then we can define a discrete location mixture. Okay, I guess I understand. So the corresponds to the stress case is discrete location mixture. Wait, what? Oh, it's discrete. Okay. Yeah. Saying something is CDF means it has properties from 2.5.3. Let me just write this down. So we're saying that let me just write. This is equal to yeah, some probability of x. I mean, okay. Like, is a CDF is actually, I'm now kind of unsure, but yeah, like saying something as a CDF, is it being able to write it as a probability like this, or is it equivalent to what is written in 2.5.3? Okay. I'm guessing you mean 2.5.3 Marcus, right? But I'm not, is it an equivalent definition? Like, I don't know. Here we assume that f of x is a cumulative distribution function, or random variable x. Then we have this. But if this is satisfied, if we have a function f such as all of this is true, do we say that f of x is a cumulative distribution function? Like, because here they define it. Here they define it as being a function from R to 0, 1, or they just define it to be a function that can be written as a probability less than some x. So it's not necessarily that it's the other way around, I would assume. But I don't know, maybe some other text define it somewhere else. Maybe this is a weird definition, I don't know. It's not rigorous. I have no idea. You tell me. Anyways, is this obvious? Okay, So this can be written as, do not remember both ways, if it is both ways, yeah. Anywho, I mean, I don't think it's equivalent since, I mean, like in this definition, we don't have like a random variable, right? I don't know. I don't know if I'm actually following it. Is it obvious? It's not hard to see that H is also a cumulative distribution function. Theorem 7.2 in Jacob and Protter says I mean, look, this can be written as less than or equal to x for a for some density, right? And we have that with the density g given the distribution. Wait, no. Furthermore, g is a density. Wait, let me just think for a moment. I guess we're now saying that the random variable is absolutely continuous. Blah 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 blah. Okay. If and only if. What does Wikipedia say? And these are the properties. Or sleep, or a good night. Now it's nice having you here. I'm gonna chat with you. I mean, like, we can. What laptop do I use? By the way, hello, Blues right here. Welcome. I don't even know. It's some HP laptop. I guess you can see it. Like, but I don't really know the exact model. I got it from my dad, so that's why I don't really know that much about it. Change your variables. But is it? I mean, if we assume it's absolutely continuous, we have that given that X is a density, so oh wait. Wait, in what way? NN18. H corresponds to a mixture of different shifted distributions. Define a scalar scale mixture distribution. Okay, yeah. Feel bad for the teacher that I learned math their whole life. I think this is actually just definition of FY. This is all definitions, no? Yeah, well, I mean, yeah, this is the definition, right? So fy is equal to this of x minus y. But how, I guess the question that I badly posed is the text says it is not hard to see that h is also a cumulative distribution function. I mean, sure, if you look at these properties, over here, I could probably, this is all just definitions, no? I mean, this saying it's, I mean, I don't really, like, this is a definition of H, yes. And is it the pavilion? Which book is it? It's in the LinkedIn description speeches. Yeah, so I mean, so here ChatGPT uses the definition of these three like properties, which is fair, I guess. I just find it a little confusing. The text doesn't really say that it's an equivalent definition or anything. Just I mean, I guess I can get by that. And then we have scaling and stuff. And we have continuous scale mixer. Okay. So we have distribution neither discrete nor continuous. So if we have x1 that is Poisson distribution, it's discrete with CDF cumulative density function f1. While x2 is normal distribution, continuous with CDF f2, and y is a mixture distribution given by that using 2.5.1. We have that probability y is fy minus right, yeah, so we can represent this probability using only CDFs, which is totally fine. And then we can use the definition of the distribution. Then we can collect the terms. The probability of x1, y, probability of x2. Therefore, y is a non-negative integer. your studies. Thanks, Marcos. I'll see you around, I guess. Good luck with your masters as well. When a variable y is not continuous, on the other hand, we have right. So the sum is not equal to that. Otherwise, mixture of discrete and continuous distribution. Okay, let's do some exercises, I guess. Let me see if there's some on the canvas page. So we have 2.5. Yeah. This book is not very intuitive. Maybe not. I mean, there are other books, but I don't know. I'll just stick with this one for now. Try not to get bogged down by too many books. This has so many parts. That's fine. Determine whether or not f is a valid CDF. Whether f satisfies properties A through D from theorem 5.2. Okay, well, no. So f of x is equal to x. Okay, I don't need to write this shit. Okay, well, obviously it's not. Or wait, what are the properties? It needs to be between 0 and 1 for all x, but that's not true. So in this, for B, have it is like this. I guess we need to have that. I guess let's just graph it so it goes up like this, then it goes up. Oh my gosh, I can't. It's like that. This is 0, it's 1. So we know that the limit as x goes to infinity of f of x needs to be equal to 1. And the limit as x goes to negative infinity, which is 0, which is good. And then it's between 0 and 1, which is good. And then we need to have that it's I need to charge my phone. Luckily I have a charger. Could you move your camera window? Can't see the question. Oh, yeah, thanks for writing that. You know, okay, let's look at OBS. I'm not even looking at the screen that much. Yeah, there you go. I forgot the last property. I think there were 4 properties. Oh, it needs to be increasing. Well, I mean... it is increasing. And C is also good. Check, check, blah blah blah. And this one is not good. No. It's not between 0 and 1. This one is, yes, it is good. 0 between 0 and 1, blah blah blah, that exists. We have that. What was the last property? That it's increasing, indeed it is. Wait, what is the difference between F and E? A, okay, it's less than 1. Well, when it's 1, it's 1. It's growing, and it's 1. This is also, it's fine. Growing, the limits are good, and it's also always between 0 and 1. And when it's negative 1, no, it's not good. I think it was 5. Okay, that problem wasn't that interesting, so that's why I kind of skipped it over. Or glossed it. Oh my god, I'm writing so big. If I compare it to my other text. Maybe I should zoom in a little. That's probably a good idea. So I have like the same font size. That would be nice. Okay, let me do it so you can see. Each of the following in terms of the function biscuits. Okay, so how do we define this? I think this was the CDF of the alright, so for little, so this is the density function, and yeah, so this is equal to negative blah blah to x of 1 over square root 2 pi e to the negative this is I think this is divided by 2 sigma squared. This is divided by sigma, I think, or some shit. Then this is x minus e square. If my memory serves me correct. So if I want to calculate a probability that y less than negative 5, we have negative 8. Pi is hiding ugly integral, don't open the definition. But how do I just use I mean, I guess I can't really calculate the integral. That's true. So I guess I just use the software. Oh, it says in the question, use table D2 or software. Okay, well I'm not gonna do that, sorry. Goodbye. Okay, 2.5.7, that's the next question. Let's, so you can see. Suppose you have a CDF of x, which is x squared. Complete each of the following. Well, I'm not gonna do this. My bad. I'm just not gonna do this. Let's just move on to the next. Oh no, we have one. 2.5.21. Okay, now we have some funky distributions that I don't really know. Weibull above. I recognize it somewhere. Weibull. So consider so the density function oh. Uh, so when they say distribution function, is it the CDF? Alright, so this is just the density and so we have that. I don't know. I guess I'll calculate it as well. I guess you just do change your variables. So we have u is equal to d is equal to and this is equal to x to the x, I guess. Or wait, No, this is not making any sense. I should have a t there instead. So I need x, or I guess in this case would be negative x. The negative limit. How long have I been live for? 2 hours? Alright, cool. Actually, I'm not really that sure. I'm guessing it would be 0. I mean, okay. I don't think this is that difficult. Wait, actually, I think this is wrong since it's just 0 otherwise. So this would just be from 0 to x. Look at the function itself. I mean, yeah, but I think these limits are wrong. Yeah, my bad. Yeah, I'm not sure what I'm smoking. I'm smoking some strong stuff, I think. Yeah, some really strong stuff. I think I just confused myself with with not having the correct integration, like dummy variables here. I confused myself. TDX here. Yeah, I just confused myself. Yeah, this should definitely be correct. And then 0 otherwise. Yeah. Does it surprise you that all information about the distribution of a random variable x can be stored in a single function? Why or why not? What other examples can you think of where lots of different information is stored by a single function? I guess it's convenient. I mean, I guess it's not really surprising, but it is convenient. One dimension chain variables. Alright, okay, what is the goal actually? Where do I want to be? So the last okay, so let's see. Okay, so it's here. I was at conditional densities of PMF. So we'll go multivariable. So joint distributions. multi-dimensional variables. I think I'm pretty much good, maybe. I'm not sure how far I should go before I catch up. But maybe I'll just stop here and I'll do some other stuff. Yeah, I think so. So what do I want to do? Let me just close my window, or like here, so I don't share anything private, which would not be good. Yeah. I want to do some one variable stuff and some like first year stuff, so I can for the exercise class I'll be holding next week. I want to do some preparation so I don't look like a fool. Let's do course content. Never mind. Course literature. I need some more water. Biscuits. Okay. Well, I guess I'll just kind of hand wave it. Okay, let me open the thing again. So I'm not really sure exactly where the students are at. Maybe I'll just download this. Yeah, so last time they were at elementary number theory. Yeah, so at the divisibility, division algorithm. But not really. So I think I'll do the Fontane equations, prime numbers, positional system congruence, and I'll probably do some complex numbers as well. Granted, I don't want to spend that much time on this. I mean, max I'll spend like 2 hours. Or, to be fair, I didn't, like when I took this course, I didn't really go through this that deeply, so I'll probably maybe spend more time than I would want to. Like compared to the one variable stuff, which is this book, or this, like, yeah, which the lecturer made. I think this is a really good book. It's called Don't Panic, and I think I can like publish it at the Discord, or maybe I cannot actually. I'm not sure if my like the lecturer will actually publish it or not. Anywho, so they were at chapter 4, I think. Wait, let me look here. All right, let me excuse the. Yeah, me not knowing what I'm doing. Okay, let me just close the statistics. Oh, it is, okay. September is the 9th month. Yeah, October, November, it seems weird. Oh no, it's not weird at all. Okay, I guess that makes sense. Okay. So the rules, limits, big O notation. Oh yeah, table of growth. Yeah, I want to prove these guys. I guess you can't really see what I'm doing. Wait, let me show it. Right, so table of growth up until table of growth. And then I'll have one more lecture, which is oh, we have page numbers. Fan-freaking-tastic. Oh, snap. Okay, well I guess that's what we're gonna do. Pages 126 to 141. And then recommended exercises. Shall probably do. Sections 4.4, 5.1. So we have okay. Yeah, so these table of growth things would be good. Okay. Like I said, I don't want to spend too much time. Okay, limits for sequences. So we have the definition of the limit of infinite series. We have some proofs, which is not really that difficult. I've already looked through this a little bit. So. Define what it means to sequence goes infinity. Yeah. I remember this was so difficult for me when I took this course. I was struggling so much. Right, the balloon lemma. Do you think I can prove it? I probably can. I don't think it's that difficult. But yeah, this is the monotone convergence theorem, and for some reason my lecturer likes to call it balloon lemma via this, since you can, I guess, view it as, I guess, if a sequence is bounded, it has a ceiling, and it's if it's monotonely increasing, then the balloon will slowly hit the ceiling. Fantastic. So yeah, if you, it's like dropping or letting go of a helium balloon. Courtesy of my lecture. That the Basel theorem must converge to some number L. Right. Yes. Yeah, so this is actually a really good exercise. So the Basel series, we can use the Oresme's trick to bound it using, we can bound it by I think we bound it by like a geometric series, and then we can use monotone convergence theorem. Use the balloon lemma in combination with exercise 3.2 to prove that the harmonic series must diverge. Oh yeah. Yeah, so you would do the you would assume that right, yeah, so you would use this like the contrapositive version, and you would do this by contradiction. I assume it does has a limit or has a bound, but we can't, like, we can approximate it by yeah, so this one is also a good exercise. Yeah, this is good. This is good. The rule book I wanted to do, because I haven't done, but I think it's really simple. Yeah, actually I did this with Cauchy series when constructing the real numbers, which I did a whole 10-page report on. I'm not sure if I'll end the stream here. Okay, no, we actually have 20 minutes left, so I'm gonna head out for a little bit. I'm gonna head to the bathroom real quick, and then we'll just continue after this for another 30 minutes. I'll try to prove some of these theorems here. I mean, in the meanwhile, maybe some of you can do these. I think these are like 1, 2, 3. I want to do the squeeze theorem just because it's nice. And then I want to do the growth chart. Alright, I'll be right back. All right, there you go. Let's continue. Less the weight. Less the weight. Okay. Let's go to home. Let's do some one variable stuff. One. No. Let's see here. Okay. Let me think. Okay, let's just write down what we have. If I want to prove number 5, it shouldn't be that difficult, right? So if you have this So if we have that biscuits. What should you do here? Okay, well, I guess maybe it is. You just. Bruh. Alright, so we know that Bn Okay, I think you can just do it like let's see here. Okay, I'll just move on since I'm not really getting it. I should actually be able to do this. A big annotation. Indeed. Okay, I think we're fine there. I don't need to spend that much time there. Even though this squeeze proof is not instantly coming to my head, I need maybe some guidance there. I think I remember there being some kind of trick. I feel like I'm just blanking there. Anywho. Actually, I don't think I need to spend time on this. I am feeling kind of good on that. So yeah. Maybe I'll actually just end the stream here. A bit of rough at the end. But maybe I'll see if there is some hint. Click, 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 click. Whatever. What did I manage to do? I did some stats, and then the last hour I struggled with. I mean, I guess I went through what I'm gonna, like the exercise, the topics of the exercise class I'll have tomorrow with the first year students. Okay, yeah, sorry. Yeah, the idea here is to... Okay, that's actually good that I went through it, because I kind of forgot where I should go. Yeah, so we want this to be less than some epsilon, and this is the same as Bn being less than epsilon plus L and less than L minus epsilon. Not very pure math. Maybe not. But this is pure math. But I guess the title is more meant to reflect the degree I'm pursuing. But anyways, and I guess we know that this is have that AN is so we pick the max, then we can have that yeah. So we pick N to be, and then we can do this. Alright. Cool beans. Okay, so tomorrow I'll focus on ODE. I'll focus on linear analysis as well, and maybe I'll do some several variable. I am gonna do a retake, like, or a oral exam on several variables 1 course to get a VG, since I kind of missed off computation on the exam. So that's, maybe I'll do that tomorrow as well. But anyways, I'll try to do a long stream, or like a 5-hour-ish stream tomorrow. So that's the goal. But with that being said, I'll just end it here, and I'll grab something to eat, and then we'll go to bed. So yeah, I'll see you guys then. I'm not sure. I'll probably do a stream later on, like in the evening. Since I'm gonna drive in the morning, and then I'm gonna go to the gym. Granted, I do also have like a meeting for the nation, so maybe I'll come home late. Alright, I'll do my best, at least 3 hours.